Data analysis projects provide a structured framework for transforming raw data into actionable investment insights. In financial applications, analysts use data analysis to forecast returns, identify risks, classify securities, and support portfolio decisions. The process begins with clearly defining the business or investment problem and determining the desired output of the model. Once objectives are established, analysts identify relevant data sources and collect information that supports the analysis. A well-defined project scope ensures that resources are focused on answering meaningful questions while reducing the risk of developing models that are statistically sophisticated but economically irrelevant. The first major stage of a data analysis project is conceptualization and data collection. Conceptualization involves identifying the target variable, selecting potential explanatory variables, and determining the type of analytical method required. Data collection follows and may involve gathering information from financial statements, market databases, economic reports, alternative data sources, or proprietary datasets. The quality of a model is fundamentally dependent on the quality of the underlying data. Therefore, analysts must ensure that data are relevant, reliable, sufficiently comprehensive, and representative of the problem being addressed. Inadequate or biased data can significantly reduce the usefulness of subsequent analysis. After data collection, analysts perform data preparation and data wrangling. Data cleansing addresses missing values, duplicate observations, inaccurate records, invalid entries, and inconsistencies across datasets. Data wrangling includes transforming raw information into formats suitable for analysis through extraction, aggregation, filtering, selection, and conversion processes. These steps are often among the most time-consuming components of a data project because real-world financial datasets frequently contain imperfections. Effective pre-processing improves model reliability by ensuring that inputs accurately reflect underlying economic relationships. Properly prepared data also reduces the likelihood of misleading conclusions and improves computational efficiency during model development. Data scaling is another important element of pre-processing. Financial variables often have different units and magnitudes, making direct comparisons difficult. Two common scaling methods are normalization and standardization. Normalization transforms values into a range between 0 and 1, while standardization rescales variables to have a mean of 0 and a standard deviation of 1. Standardization is less sensitive to outliers but assumes a roughly normal distribution. Scaling helps machine learning algorithms perform more effectively because variables contribute proportionately to model estimation. Without appropriate scaling, variables with larger magnitudes may dominate model outcomes regardless of their true economic importance. Data exploration seeks to understand the characteristics, quality, and structure of the dataset before model construction. Analysts use descriptive statistics, visualizations, correlation analysis, and summary measures to identify patterns and relationships. Exploration helps detect outliers, unusual observations, missing values, and potential errors that may influence model performance. It also provides insights into variable distributions and potential nonlinear relationships. In investment applications, exploratory analysis may reveal hidden trends, sector-specific characteristics, or behavioral patterns within markets. By understanding the data before model training begins, analysts can select more appropriate modeling techniques and improve overall predictive performance. Model training involves fitting an algorithm to historical data so that relationships between inputs and outputs can be learned. Training data are used to estimate model parameters, while validation techniques assess how well the model generalizes to unseen observations. During training, analysts must balance predictive power with model complexity. Models that are too simple may underfit and fail to capture meaningful relationships, while excessively complex models may overfit and perform poorly outside the training sample. The objective is to identify a specification that accurately captures underlying patterns while maintaining robust predictive ability in future applications. Model evaluation measures how effectively a trained model achieves its objectives. For classification problems, analysts construct confusion matrices and calculate metrics such as accuracy, precision, recall, and F1 score. Accuracy measures the proportion of correct predictions, precision evaluates the reliability of positive classifications, recall measures the ability to identify actual positive outcomes, and the F1 score balances precision and recall. Receiver operating characteristic (ROC) curves further assess classification performance by illustrating the trade-off between true positive and false positive rates. These metrics provide a comprehensive assessment of model effectiveness beyond simple prediction accuracy alone. For continuous prediction problems, evaluation commonly relies on root mean squared error (RMSE), which summarizes forecast errors into a single metric. Lower RMSE values indicate greater predictive accuracy. Following evaluation, analysts engage in model tuning by adjusting hyperparameters to improve performance. Techniques such as grid search automate the selection of optimal hyperparameter combinations. Ceiling analysis can further identify weak components within the modeling pipeline that limit performance. Ultimately, successful model development requires continuous refinement, balancing bias and variance, and ensuring that the model remains economically meaningful, statistically robust, and capable of generating reliable investment insights in real-world decision-making environments.